All right, today we're going to be looking at the paper Noise-Induced Barren Plateaus and Variational Quantum Algorithms. And as usual, we'll just be sort of briefly overviewing it before going into some example code. So noise-induced barren plateaus is a phenomenon slightly different than the barren plateaus that you may be familiar with. And that is outlined very well by this figure 1 here. So in traditional barren plateaus, right, we have our objective function that becomes increasingly plateau-like, right, where it becomes flat. So the gradients, the gradients which are expected value 0, the variance drops exponentially, which is problematic because if our landscape is flat, we can't traverse it. However, what it usually looks like in these landscapes is, if I do a little drawing, is right, if this is a 1D representation, right? So this is normal barren plateaus. Let's say this is our cost function. Normally we have barren plateaus. Ooh, that's a, and then we have this, right? And so you can't, so this is obviously our cost and just some theta. And so if you're like right here, oh my gosh, this is a very sensitive mouse setting I have right now. You're never going to be able to use the gradient information to get down here because it's too flat. Whereas noise-induced barren plateaus, it's a different kind in a sense that, as you can see here, as the problem size grows, this becomes not flattened like this, but entirely, I guess, squashed maybe. So it just becomes like that. Obviously, this is a huge, exaggeration, but you can see the difference between these two, which are not the same. And this figure, I think, highlights it well, where the noise-induced barren plateaus is a flattening of the cost, not just a flattening of the landscape around the cost. And so in this paper, their main result, which we won't talk too much about the derivation of, is in theorem 1, which is right here. Basically that, you can look at that, but as they summarize here, that the magnitude of the gradient decays exponentially with L. And here L is, of course, the number of layers, because intuitively, right, as a number of layers, we assume that each layer is sort of the noise-inducing operation. And so depth is clearly going to be the important factor in noise-induced barren plateaus. Assuming that we have no like depth increase, right? Assuming our circuit's ansatz scales O of 1 with qubit size, the amount of noise, right, if I do a 1 qubit gate here, is presumably going to be the same as if I have n 1 qubit gates operating simultaneously. So that's also something worth considering. And in this, you can see, right, this is the exact framework I was talking about, where with each of these operations, you're introducing some noise. And that noise can basically, right, it's disrupt the optimization in the sense that it prohibits you from getting as much information from the circuit as you would before, which makes the optimization harder. So there's lots of nice proofs here, which, I cannot verify. I'm not going to have the time or necessarily the knowledge to verify that these are, good, but obviously I assume they're a-okay. And now we can see the results that we're going to be looking at in the code. And this is for QAOA. And you can see that they consider 3 different scenarios. One is, of course, noise-free, which is the traditional, simulations we're used to. One is noisy training with a noise-free final evaluation of the cost. And then one is noisy training and noisy final evaluation. You can see here that as this is for a constant qubit size, 5 qubits, as we increase the number of layers, even if the training or even if the evaluation is noise-free, past a certain point around p equals 6, this goes downhill. So it becomes disadvantageous to add layers at that point. And almost immediately we can see with noisy training, it becomes disadvantageous to add layers. So this is because we have two competing forces here. And this is an interesting, more general question is, with increasing layers of any sort of variational algorithm, we generally expect better performance, right? Because we're sort of creating more the expressibility in our circuit in general. Obviously, some circuits are all perfectly expressible with whatever one layer you want to do. But in general, right, we, for example, with QAOA, we expect better performance with more layers. But then better performance also increases the amount of noise, because every layer has noise in addition to the constant noise, right? Qubits naturally decay over time. So the question then becomes, we have these competing objectives of more circuits is better, or more layers is better performance, but at the same time, more layers is worse performance. So evaluating these two competing objectives is often a challenge of near-term variational algorithms. And so, and this is what this highlights really well, is that you can see right here, the trade-off point occurs really quickly. And this is also observable on, for example, real hardware. They run it on Montreal, which is a IBM superconducting qubits. And so that's basically the big takeaways. I'm not going to spend too long talking about the theory because, we all care about practice. So let's dive into the practice. The first thing I'll note as I go over here, just make sure that, yep, this is sharing, is that the results you're going to see here are not as good as I would usually like to present. And this would be something I would go back and workshop more to get sort of the results that I would like. However, this is perhaps the first, this is the first video, I guess, that I've ever spent like real money on, in the sense that these computations for noisy simulators take forever. And I didn't want to run them on my laptop. I kind of destroyed my last laptop by running a lot of experiments on it. So I was like, I'm just going to get some cloud compute and just run it on there. And so you can see, I'm not a very good with cloud compute or resources. Like my knowledge of them is not extremely high on how to use them. Like the theory, okay, but the actual practice of like using them is not always super high. But you can see if I share this is a little screenshot of my billing tab. So you can see I did spend $41.58 using a compute service that I've used before, actually, and had some success with, called Lambda Labs. No, they are not sponsoring this video. But if you want to give me free compute, I take that. I don't think anyone from Lambda Labs is watching, but I always like free compute. I'll run my experiments on it. But I used this before with some work. For example, when I was working with my Unitary Fund grant, I used Lambda Labs for the compute. I was having some struggles though, like with connections getting reset. My programs weren't running as long, but yeah, I don't know. It's not super important, but that is why you're going to see these results and be like, these are kind of whatever. But because I spent $40 on them, I kind of want to, share them because the code is sort of still valuable in itself. So we have a lot of standard QAOA boilerplate code that I've copied from previous videos / existing, things I've written. We have our usual mixer and cost Hamiltonians for max cut, which is the C0 RZ C0 for the ZZ exponentials, and then the RX rotation for the X mixer. We have our cost function, of course, which is just the ZZs. And then we create our circuit by starting in the equal superposition state and then adding cost and mixer Hamiltonians sequentially. We can make our QAOA object in TensorFlow-Quantum with our standard qubits, and then depending on what the noise level is, for noiseless, obviously I don't want to waste time with parameter shift because it would give me the same results, so I'm just going to use adjoint differentiation. But for noisy ones, I do in fact use the noisy PQC model and use repetitions of 1,000 with the parameter shift differentiator. The first thing I'll note right away is that this model of noise is in fact different from what's used in the paper. If we scroll all the way down, oh, this is different. I was looking at the Nature version before. Let me bring that one up. That'll be easier just to compare to. Oh, actually, it's right here. So the noise model was the sort of, you can do like, I assume this is, it says, was obtained by performing 1 2-qubit gate set tomography on 5, which basically sounds like the IBM Quantum has fake backends you can use in Qiskit, which are like the noise models of a certain backend. So that sounds like more what they're doing. I am just using depolarizing noise. Now, to be fair, it's not as accurate as this sort of noise model, but at the same time, it is a kind of, it is a noise model that exists and is also not terrible. And there are ways you can get it to be closer to hardware. There was a paper on QSIM and Circ and simulating noise and depolarizing noise versus different noise models that I'll be sure to link it below. And that's where I got the 0.01 as my number from, is from this paper as saying this is sort of like kind of close to hardware noise. But that will be, of course, in the description. And so that's the first difference. The other difference you'll notice right away is that, oh, it looks like there's a typo right there, is that it was used on an optimizer based on Nelder-Mead simplex. So I don't know what that is, right? I know what Nelder-Mead is. I don't know what it is based on it, but the gradients are much faster in TensorFlow-Quantum. Obviously, you could wrap it easily in a sort of SciPy optimize minimize function, but I don't know if that would be any faster than the TensorFlow-Quantum. Nelder-Mead, of course, like parameter shift scales O of n in the parameter space to evaluate. And so that is another difference. I don't know, that is a possible impact. I would encourage you to try replacing this code with Nelder-Mead and see what happens. Nelder-Mead can actually perform pretty well. You can check out my review actually on evaluating the relative performance of different optimizers. I thought I made a video on it, but now that I'm thinking about it, I realize maybe I haven't made a video on that, in which case that would be an excellent idea for me to make a video on. Yeah, I'll have to look. I'm just thinking of that right now. So anyway, you can see the differences already, but those are the last. That's pretty much the two main differences, but those are big. So anyway, getting back into the code, we have our standard training function. We train using Atom for the standard 100 iterations. You could increase this as well if you're interested in playing around with it. And then we have our function to get the ratio. So what do we do here is we sample from the circuit either in a noisy or noiseless manner, and we then compute the true max cut and then compute our average cut size over the true maximum cut size, and that's what's known as the approximation ratio. There's another way, I guess, you could measure it. This is the average cut. You could also take the maximum or the most likely cut, right? So this is the expected value, I guess, of the approximation ratio. But if you just took the max, you might get different results here. And so that's, I guess that's it, right? If you took the most probable bit string rather than the average, you would get probably different results. So moving on, we have our training routines here to recreate two figures. We have, if I scroll up, we're going to be looking for these two right here. So we have this one, which is varying depth, and this one, which is varying qubits. So we can vary the depth from 1 to 20, as they do here. Should probably be 21, being honest, because Python does not include the last one. And then we make the graph. This is, of course, as somewhere in here is mentioned that it's a random graph with problem size and varied number of rounds. yeah, we can see here 100 graphs are generated Erdős-Renyi graphs such that each graph is chosen uniform. So it's uniform, which means the probability of each edge is 0.5. And this is the Erdős-Renyi graph generator. We make the graph, we get the results, and we repeat this process for however many. In this case, I only did 50 instead of 100. And we do that for each of our noiseless evaluation, noisy eval, and noisy train, and all of that. Then when we plot the results, we can see this. And we'll notice prior to the, if I scroll over here, back up. Oh, oopsie, scroll down. So this is basically a subset of the graph from here to here, basically, is what we're looking at. We can see that the black does increase, as it does here, to 0.9 at 5, which is slightly worse, but then there's a plummet here. I don't know what's going on here. This is interesting to evaluate, but we can see the same trajectory before this. This might be a little, I might have saved the wrong results or something. I don't know what's going on here. And then we can see that just like in the paper, the noisy train and eval peaks at 2, and then the performance degrades over time. And so we can see that here. We actually can't see the exact results. They would be, right here in the graph. But we can see the same trend, which is okay. And so obviously you want to get more results. The code is here and it should probably work to do that. Then for the next section, we have the qubits we're varying and keeping the depth at 4. We have the same exact code here just to generate the graphs, but this time with n qubits instead of a static amount. And this is, we have a solid 2 data points. It's worth noting that these qubits start at 4. So I should do +4, not +1. And we can see this is not particularly interesting, but it kept crashing. So like my cloud access, not like the code. The code would always run, but then I would get errors in the cloud compute. So it's not the code's problem. It's somehow I was using cloud compute wrong, which is not surprising. And so we can see the same, the trend is there. Obviously extrapolating a trend from 2 data points is, not a good idea, but we're doing it anyway here. We're rebels. And we can see that starts at 0.1, goes to 0.95, which is, as you can see, slightly this is slightly below that, but the relative performance, I think, it looks, I don't know, I think the trends look similar, but obviously I encourage you to run it more and get better results. And so yeah, that's pretty much it. Of course, the papers and code will be in the description. I know the results aren't as exciting, but hopefully they're still somewhat interesting, and maybe you can do more with them and play around to get better results.